it sort of shakes, it almost disrupts the vacuum of space and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. The laws of nature that we use to calculate what happens tell us that information is never destroyed. And when you calculate what happens, it tells us that information is destroyed. So that's why everyone got interested in it in the 80s, because it's interesting.
What if the universe isn't as solid as we think? What if everything we know about reality, space, time, even the laws of physics, is just a surface layer? What if, in our quest to understand the cosmos, we've accidentally poked a hole through it? That's not science fiction anymore. Deep beneath the border of France and Switzerland, scientists at CERN may have created something unthinkable, a microscopic, human-made black hole. But it didn't just collapse and vanish, it behaved strangely. It left behind clues that something deeper, something unseen, might be lurking beneath the universe we thought we understood. This isn't a clickbait headline or speculative sci-fi. Peer-reviewed theories for decades have predicted such a moment, and now the moment may have arrived. So what exactly happened at CERN? Why are some scientists whispering warnings? And what does this mean for the fabric of reality itself? The day reality glitched. The synthetic black hole in CERN's Large Hadron Collider, protons collided at nearly the speed of light. That's standard, but what followed wasn't. Among the showers of particles and energy signatures, researchers spotted something that shook them, a minuscule point where space-time itself collapsed, even for just a fraction of a trillionth of a second. To their astonishment, the data aligned with theories predicting the creation of a micro-black hole. This wasn't just another experiment. This wasn't just more data. This was a possible tear in reality. According to the standard models, such black holes shouldn't form at these energy levels, unless hidden dimensions exist. Theories like the large extra dimensions model suggest that gravity could be leaking into unseen spatial realms. If true, this experiment didn't just prove a particle physics theory, it revealed a deeper architecture of the universe. What happened after the black hole evaporated only deepened the mystery. The decay signatures didn't match predictions. The energy dispersal, the patterns, it all hinted that something unknown was at play. Physicists weren't just facing a breakthrough, they were staring down a rewrite of how reality works. Wormholes, entanglement, and the edge of physics. What happens when you smash open the boundaries of reality? You get questions nobody's prepared to answer. As the synthetic black hole vanished, the particles it left behind weren't random. They were correlated in ways conventional quantum mechanics can't explain. This brings us to a controversial theory, ER=EPR. It's the idea that Einstein-Rosen bridges, aka wormholes, are literally the same thing as quantum entanglement. Two particles connected at the quantum level might actually be linked by tiny wormholes in space-time. This black hole, for a micro-instant, might have served as a quantum bridge, linking regions of space-time in ways we've never observed. There's more. The decay pattern could provide the first real-world data to probe the information paradox Stephen Hawking raised. Is information lost forever in a black hole, or encoded in its radiation? The anomaly might hint that information can be preserved, possibly solving a debate that's raged for decades. And then there's the firewall paradox, a mind-bending clash between Einstein's theories and quantum information. Some scientists are even suggesting the black hole had soft hair, a weird quantum property that stores information at its event horizon. These aren't fringe theories anymore. The data is here, the mystery is real, and the implications could rewire our understanding of physics at the most fundamental level. Cracks in the vacuum. Did CERN stress reality? Now here's where things get unnerving. Physicists didn't just measure the black hole's birth and death. They measured its effects on the vacuum of space itself, the so-called nothingness that fills the universe. But quantum physics says this vacuum isn't empty, it's metastable, like a ball balanced in a shallow valley. Hit it hard enough and it could tumble into a deeper valley, a vacuum decay. If that ever happened, it would rewrite the rules of physics, spreading a bubble of new reality across the universe at the speed of light. CERN's experiment didn't cause that. We're still here, but the data showed tiny fluctuations, like reverberations in the vacuum. Think of a bell ringing after being struck. Some theoretical physicists believe this suggests the vacuum was disturbed, just slightly. Still, the fact that it responded at all is deeply unsettling. It forces us to ask, what's the limit? What happens if we keep pushing harder, colliding particles with more energy, more precision? Are we slowly testing the structural limits of reality? The implications are no longer just scientific. They're philosophical. Playing God or playing smart, the ethics of discovery. When news of the micro black hole broke within the scientific community, the reactions weren't all celebratory. A quiet but fierce debate erupted, not about whether the data was real, but whether the experiment should have been done at all. This taps into a philosophical dilemma known as Pascal's mugging. How do we weigh low probability risks when the stakes are unimaginably high? Philosopher Nick Bostrom argues that even a 1 in a billion chance of destroying the universe makes such experiments morally questionable. After all, if there is even a tiny chance that we could cause a vacuum decay, do we have the right to risk it? But on the other side, physicists like Brian Cox and cosmologist Martin Rees downplay the risk. They remind us that cosmic rays, which strike Earth's atmosphere with far more energy than the LHC can generate, haven't triggered any apocalyptic chain reactions. If nature's been doing this for billions of years, they argue, our man-made collisions are hardly new. Still, the tension remains. Are we blindly charging into the unknown, or courageously unlocking secrets essential to humanity's future? What's certain is that the boundaries between science and philosophy are now more blurred than ever. Because this isn't just about particles and formulas, it's about our collective responsibility to the universe we inhabit. Ghost particles and dark secrets. While the creation of the black hole stole the headlines, the real shocker might be what came out of it. When black holes evaporate via Hawking radiation, they're supposed to emit a well-understood mix of particles: photons, quarks, gluons, standard stuff. But this black hole didn't play by the rules. Its decay trail showed unidentified energy signatures, particles that didn't belong to any known category. Could these be gravitons, the elusive carriers of gravity? Or even stranger, could they be particles from the dark sector? That's the hidden 95% of the universe: dark matter and dark energy. We've never seen them directly, only their effects, how they bend light, how they tug on galaxies. But now, thanks to CERN's micro black hole, we might have finally caught a glimpse. Some theorists believe this could be the first indirect proof of primordial black holes. Tiny black holes formed just after the Big Bang. That may account for dark matter. If CERN's results align with those predictions, it means we've bridged the gap between particle physics and cosmology. Machine learning systems at CERN are now scouring the data for non-classical correlations, looking for signs that reality itself was warped during the experiment. The simulation question: have we gone too far? At this point, we're no longer just talking science. We're talking existence. When you create a micro black hole that disrupts space-time, hints at hidden dimensions, and maybe even leaks information, the question becomes unavoidable. What kind of reality are we living in? Some philosophers and physicists now dare to ask, is the universe a simulation? If we can create conditions that weren't supposed to exist outside the Big Bang, if we can bend the rules of space and time in a lab, does that mean those rules are programmable, exploitable? Theories like the holographic universe or digital physics suggest we might live in a reality that's computed from a deeper layer of information. And CERN's findings only add fuel to that fire. The very act of creating a synthetic black hole means we've crossed a line, from observation to manipulation. We're not just mapping the universe, we're rewriting it, even if only in microseconds and microscopic scales. So what happens if we tear the wrong thread? This section isn't about answers, it's about awe. Because the deeper we go, the more the universe looks less like a machine and more like a message waiting to be decoded. Gravitational whispers and reality's ring. We often think of gravity as something simple, what keeps us grounded. But in the realm of black holes, gravity isn't just a force. It's a ripple through the very fabric of space-time. When the micro black hole at CERN vanished, researchers theorized it might have emitted gravitational waves, microscopic versions of the ripples detected by LIGO during massive cosmic collisions. But these weren't star-sized events. These were subtle, quantum-scale murmurs, so faint they slipped past our current detectors. What's more chilling is what came with those waves. The vacuum of space, The very field that defines what nothing is, reacted. The quantum field around the collision site shimmered unnaturally, like a bell ringing after being struck. Physicists call this vacuum instability. While the disturbance wasn't catastrophic, it raised eyebrows. If we can tickle the universe hard enough to make it ring, what happens if we strike it harder? Are we gradually approaching a tipping point? This event might have been harmless, or it might be the first warning tremor. Because every time we escalate these experiments, we're asking, how much reality can handle before it breaks? Black hole theory, from equations to evidence. Let's rewind for a moment. The idea of creating micro black holes in a lab isn't brand new. Theoretical physicists in the late 90s and early 2000s proposed it, but only under very specific conditions. Back then, the energies required were thought to be impossible. Under classical physics, creating a black hole would need the power of 1019 G, a scale beyond any human machine. Then something changed. New models like Randall Sundrum in ADD, Arkani Hamed, Dimopoulos, Diwali suggested the universe may have extra dimensions, and gravity might leak into them. That would mean our required energy threshold drops drastically, down to the levels CERN can reach. That's why the Large Hadron Collider, which once seemed too weak, suddenly became the perfect lab to test these theories. So when particles collided at 13 TeV and a strange signature showed up, it wasn't random. It matched predictions, down to the femtometer scale, evaporating in 10 to 27 seconds, releasing jets, photons, leptons. Only this time it wasn't just math on paper. It was real, measured, observed. The equations weren't just describing imaginary possibilities anymore. They may have described our actual universe, the world's reaction, panic, praise, and polarization. Once the whispers about CERN's potential black hole made their way into the public, the reactions were dramatic and divided. Within the physics community, the mood was cautiously electric. Some researchers described the moment as bigger than the Higgs boson. If confirmed, it would validate decades of theoretical work and unlock a new frontier of physics. For those who'd spent their lives on fringe theories, like extra-dimensional models or quantum gravity, it was a moment of vindication. Their ideas were no longer speculation. They might be the blueprint for reality. But philosophers and ethicists saw something else. A boundary being crossed. Were we now manipulating forces too profound to fully grasp? Some warn this might be humanity's Manhattan Project moment in fundamental physics, where understanding reality could come with unintended consequences. Meanwhile, the media scrambled. Some reports handled the science responsibly. Others twisted it into sci-fi nightmares, talking about Earth-eating black holes or reality collapse. CERN pushed back hard, reminding everyone that cosmic rays slam into Earth daily with higher energies. If a threat existed, we'd have vanished long ago. Still, public fascination grew. For the first time in years, particle physics was headline news, and everyone had an opinion on what it meant to poke holes in the universe. Beyond the particle, the threshold we've crossed. So what does all this mean? It means we've crossed a threshold. For centuries, science has been about observing nature, watching the stars, decoding the atom, tracing the invisible forces that shape our world. But now, we're not just observers anymore. We're creators. If CERN truly did create a synthetic black hole, even one that lasted for less than a trillionth of a second, it represents a fundamental shift in humanity's relationship with reality. We didn't just observe something natural, we made something that warps space and time itself. And that changes everything. This moment isn't just a scientific breakthrough, it's a philosophical inflection point. It forces us to ask, if we can tear holes in space-time, what else is possible? Can we rewrite the laws of physics? Could we reach beyond our universe into others? Theories once dismissed as fringe, simulation theory, holographic reality, hidden dimensions, are now being taken more seriously than ever. And perhaps most unsettling of all, this wasn't the end, it's the beginning. The next run of the Large Hadron Collider is already being planned. More energy, more collisions, more data. And with it, the possibility that we may unlock the next great mystery, the dark matter that holds galaxies together, the quantum code that structures space itself, or perhaps something we haven't even imagined. In pushing the frontier, we might just redefine what it means to be human. If you've made it this far, you're not just curious. You're a seeker of truth, and you've just witnessed a moment where science doesn't just answer questions, it reshapes the ones we dare to ask. So what do you think? Are we unlocking the secrets of reality, or knocking on doors we were never meant to open? Let us know in the comments. Don't forget to subscribe, like, and turn on notifications, because next time we're diving into how quantum computers might finally crack the mystery of dark energy and what that means for the universe's fate. Until then, stay curious, stay bold, and remember, the universe is far stranger than we ever imagined, and we've only just begun to understand why.